Okay, so today we are diving deep into some heavy-tailed data.
Literally heavy tail.
Yeah, really heavy.
Yeah, we should get a scale.
We need like a metaphorical forklift for this one.
You know what I mean?
Because we're looking at a research paper
A paper.
all about how to wrangle data when it doesn't behave nicely.
Exactly. And this isn't just some theoretical stuff.
No way.
This has huge implications for how we understand things like
Get me with it.
financial markets,
Ooh, yeah.
how ideas spread online,
Okay, contagious ideas.
even things like extreme weather events.
So like when those bell curves we all know and love.
Please, the bell curve.
Huh, you know what I mean? Those nice, neat distributions, they go out the window.
They are gone.
Because suddenly you've got these outliers, these extreme values that can really mess with your analysis.
Yeah, it's like trying to figure out the average height of a group of people.
Right.
And then LeBron James walks in.
Okay, so you're saying I'm bringing down the average.
No, not at all.
Just a little.
But you get the point. Those outliers, those heavy tails.
They've changed the whole game.
Exactly.
So how does this paper actually help us deal with these data curveballs?
Well, they focused on something called sample correlation matrices.
Okay, I'm already lost.
Stick with me here.
All right,
Imagine you have a spreadsheet,
I'm good with spreadsheets.
and each column represents the price of a different stock.
Okay, got it.
Now, a sample correlation matrix basically tells you how likely those stock prices are to move up or down together.
So it's like a cheat sheet for seeing which stocks are statistically tied at the hip? Interesting. So we can use this for stocks, but it's not limited to just finance, right?
Oh, absolutely not.
I bet this kind of analysis pops up everywhere.
Everywhere. From genetics research to understanding consumer behavior, you name it.
So we're talking about understanding relationships?
Relationships, patterns, connections, it's all connected.
Okay, I'm starting to see the bigger picture here.
Good.
But let's get back to this paper.
Yeah.
They found some kind of magic formula or something that helps us make sense of this heavy-tailed data.
Sort of. They identified a specific condition that lets us know when we can analyze this tricky data using a much simpler method than usual.
Wait, so you're saying we can take a shortcut?
In a way, yes.
And this shortcut works even if we don't know all the ins and outs of the data itself.
That's the beauty of it.
Okay, now you got my attention.
I thought you might be interested.
So how did they crack this code?
Well, one of their secret weapons is a statistical tool called resampling.
Resampling. That sounds kind of like recycling.
Kind of, but instead of recycling plastic, we're talking about data.
Okay, I'm listening.
Imagine you take your original data set
Right.
and you create a bunch of smaller randomized versions of it.
Mini-me's of the data.
Exactly. By analyzing all these mini sets, you can actually get a more accurate picture of the overall patterns.
Even with those pesky heavy tails trying to throw things off.
Especially with those heavy tails. It's like taking multiple snapshots of a moving object to see it from all angles.
So instead of putting all your eggs in one basket, statistically speaking,
You're spreading the risk, making the analysis much more robust.
I like the sound of that robust data analysis.
And what's amazing is that they found that by resampling this way,
Yeah.
they could accurately analyze the data even when those extreme values were present.
Sneaky. They found a way to outsmart those outliers.
In a way, yes.
Yeah.
They outsmarted the outliers.
But they didn't stop there, did they? This paper goes even deeper.
It always goes deeper.
Because they also discovered that the shape of the data itself plays a crucial role.
You're on fire today.
Well, I do my best.
It's all about symmetry.
Symmetry. Like how symmetrical my face is.
Sure. Just kidding. But okay, symmetry in data, what does that even mean?
It means that the data is balanced in a certain way.
Balanced. Give me an example.
Think about stock market data.
Okay, volatile, unpredictable.
Exactly. It's often pretty random with those big swings up and down.
The Wall Street roller coaster.
But now think about data on social connections. Like who's friends with whom on social media.
Precisely. That kind of data tends to have a built-in symmetry. If I'm friends with you.
Then chances are you're friends with me back.
Exactly. It's a two-way street.
So if the data has that inherent balance, this new method becomes even more reliable.
You've got it. They found that with symmetrical data, their method not only worked,
It gets better.
it actually converged on an accurate result much faster.
So we're talking faster, more reliable analysis, all thanks to a little bit of symmetry.
Don't underestimate the power of symmetry.
This is where it gets really interesting, though,
Oh, I
because
don't.
to handle all of this, they had to bring in some serious mathematical firepower.
They weren't messing around.
I'm talking about things like Dyson Brownian motion.
Now we're talking.
Hold on, did we just wander into a physics lecture?
Maybe just a little bit.
Amazing, because now I'm really lost.
Don't worry, it's not as complicated as it sounds.
I appreciate that.
Imagine trying to understand how randomness itself evolves over time.
Okay, that sounds kind of deep.
Think of those chaotic stock market graphs with all the peaks and valleys.
Yeah, I'm picturing it.
Dyson Brownian motion gives us a way to model that evolution mathematically.
So even randomness has to follow some rules, some kind of underlying pattern.
Precisely.
Yeah.
And that's what makes this research so groundbreaking.
So we've got our shortcut with this special condition, and now we have this way to model randomness itself.
We are on a roll.
This is getting good, but there's more, isn't there? They also mentioned something about this problem being self-normalized.
Ah, you notice that.
Well, it's not every day you see the word self-normalized in a research paper.
That's fair.
So what does it actually mean in this context?
Essentially, it means their method is less sensitive to some of the quirks or inconsistencies that might pop up in a dataset.
Quirks, inconsistencies. You're talking about my data analysis style.
Not at all.
Yeah.
But you see, data from the real world can be messy.
Messy is an understatement.
And this self-normalized property makes their method much more robust.
Robust. I like the sound of that. It's like a statistical all-terrain vehicle.
I like that analogy.
Oh.
It can handle a wider range of data landscapes.
So we've got our shortcut, we've got our robustness.
We are on a roll.
But there's one more thing that caught my eye in this paper. They mentioned something called shot statistics.
Ah, yes, shot statistics.
And I'm not going to lie, that one went completely over my head.
No worries, it's a bit of a niche topic.
But for those of us who aren't statistics whizzes, can you give us the elevator pitch on shot statistics?
Well, imagine you're trying to analyze the relationships between different stocks during a period of high market volatility.
Okay, so like a market crash.
Exactly.
Yeah.
Lots of those heavy tails we've been talking about.
Got it. So things are going haywire.
And shot statistics give us a way to measure the correlations between those stocks, even with all that chaotic market movement.
So it's like a financial crystal ball that can see through the chaos.
In a way, yes.
Hmm.
And what the paper found is that their magic condition tells us exactly when using these shot statistics will give us reliable results.
Even when the market feels like a roller coaster.
Precisely. It helps us make sense of the chaos.
I'm starting to see the light here.
Good.
But we can't forget about the heavy-duty math they used to tackle all of this.
Oh yeah, the math gets pretty intense.
They briefly mentioned something called a Gaussian divisible model.
Ah, yes, a classic.
And to be honest, I have no idea what that means.
That's understandable. It's a fairly advanced concept.
But in layman's terms, can you give us a sense of what it's all about?
Sure, think of it this way. Imagine you're trying to have a conversation at a rock concert.
Loud and chaotic.
Exactly. There's so much noise that it's hard to hear anything.
Been there, done that.
A Gaussian divisible model is like noise-canceling headphones for your data.
So it helps us filter out the noise and focus on the signal.
Precisely. It helps us tame the wildness of the data.
By introducing a bit of controlled randomness.
You got it.
Yeah.
It's like adding a little bit of white noise to drown out the other noise.
That's a clever trick.
It's a powerful tool for dealing with heavy-tailed data.
So we've got our shortcut with this magic condition.
Right. And now we have this noise-canceling technique.
We are well equipped.
This paper is like a Swiss Army knife for heavy-tailed data analysis.
I like that analogy.
But it's not just about the pills themselves, is it? It's about what we can do with them.
Exactly.
We're talking about understanding financial markets.
Predicting viral trends.
Even anticipating those extreme weather events we talked about earlier.
It's about making better decisions in a world that's increasingly complex and unpredictable.
So what you're saying is this research has the potential to really make a difference.
Absolutely. It's not just theoretical. It has real-world implication.
I'm convinced.
Yeah.
But before we get too carried away, I want to make sure our listeners are picking up what we're putting down.
Makes sense.
So, in a nutshell, what is the biggest takeaway from this paper when it comes to heavy-tailed data? For me, it's the realization that we don't always need a perfect understanding of the data to extract meaningful insights.
We can work with what we've got.
Exactly. Even when the data is messy and unpredictable, we can still find those hidden patterns.
It's like finding your way through a maze even without a map.
Precisely.
Yeah.
And sometimes those unexpected detours lead to the most interesting discoveries.
Now that's a thought-provoking way to put it.
Just like in a maze, sometimes the most direct path isn't always the most rewarding.
I like that analogy.
It's all about embracing the journey.
Speaking of journeys, we've been focusing a lot on linear relationships in this discussion.
Right, those correlations.
But we both know the world is rarely that simple.
True things are usually a bit more tangled.
So where does that leave us? Is this research on linear relationship just a stepping stone to something bigger?
That's an excellent question,
Yeah.
and it leads us to a very exciting possibility.
You're right. It's rare that anything is ever simple in real life.
It's true.
We've spent all this time on linear relationships in the data.
Right, because they are the easiest to model.
But the real world is way more complicated than that.
You said it.
It's messy. It's unpredictable.
Connections that go in every direction.
Exactly.
Yeah.
So where does that leave this research?
I think it's a starting point.
Okay, a foundation.
Yeah, we've dipped our toes in the water with these linear relationships.
Learn some new tricks along the way.
Now we can take those tools and start exploring those more intricate connections.
The ones that aren't so easy to define.
Exactly.
Yeah.
The non-linear relationships.
So it's like we've been practicing our archery skills on a still target.
Yeah.
And now it's time to try hitting a moving one.
I like that analogy.
We're ready for a challenge.
And I think that's a great takeaway for our listeners today.
Oh, yeah.
We've just scratched the surface of what we can learn about heavy-tailed data.
There's so much more to explore.
But we have the tools and the techniques to do it.
We're not afraid of a little complexity.
Bring on the heavy tails.
Oh, that's a wrap, folks.
Until next time.